All right. Well, thank you everyone for joining us. Welcome to our live Ask Mayfield Anything on voltage drop. This is a monthly live Q&A session that we're hosting in order to help share information on different technical topics. My name is Jennifer Alfsen, and I will be the moderator today. I am the Director of Business Development for Mayfield Renewables. And I'm joined here today with Ryan Mayfield, the CEO of Mayfield Renewables, who has been in the industry for quite some time. You might recognize him from the NABCEP conference that he just did last week. He is an expert in code compliance, particularly with applying NEC as it relates to PV system design and energy storage, which is what we do at Mayfield Renewables. And we also just launched a technical services. I'll talk more about that. But welcome, Ryan.
Hey, welcome everybody. Thanks for joining in. Glad to be doing this again.
Yeah, thanks for hosting this this session. And we are also joined today by Paul Grana. He is the co-founder and chief revenue officer of Folsom Labs, where he leads the business development, marketing, and support efforts. Paul also organizes the Solar Software Summit, an annual conference dedicated to software tools for the solar industry, organized in partnership with GTM Events. Previously, he ran product marketing at Tigo Energy, EIQ Energy, and Abound Solar, and is the lead inventor on a patent regarding combiner box design. He holds an SB in mathematics from the University of Chicago and an MBA from Harvard Business School. Thanks for joining us today, Paul. It's good to see you.
Thanks, Jennifer. We should also add, for those in the Bay Area, they will know that I, in happier times, used to run the Solar Drinks, which is also known as the silver medal to the gold medal of solar beers that used to be yours in happier times. So looking forward to the days when we can both be doing those events in the future.
Yes, me too. I miss being able to go and socialize and share beer with you, and we will definitely have to bring that back. I'm contemplating hosting a virtual beer club, so I'll let you know when that happens. And on the line as well, sitting patiently and quietly, is Lucas Miller. He is also on the Mayfield Renewables team. He is our digital strategist, where he works with PV manufacturers and service providers to create high quality technical content, such as product guides and technical presentations for webinars and conferences. And he is what I like to call my protege. I've been training him up to slowly but surely replace a lot of the work that I've been doing. And prior to joining Mayfield Renewables, Lucas spent 3 years as a marketing manager and project coordinator for a Portland-based residential and commercial PV contractor. He also sits on the board of directors for Solar Oregon. Lucas holds a bachelor's of business administration from the University of Wisconsin and is currently working towards a degree in renewable energy engineering from the Oregon Institute of Technology. And thanks for being on the line, Lucas.
Thanks, Jennifer. And thanks to everyone who's tuning in. We're really excited to dive into this topic this month.
Yeah. And so with that, going into our, I guess I should have been scrolling through our faces, but you can still see our faces on here. So these were us, and I already went through that. So our topic today is, what is the 2% voltage drop? So this is actually based on a blog article that Lucas and Ryan and another colleague of ours, Nikki, wrote on what is thought of as a rule, which is not actually a code rule. So can you tell us a little bit more about just the topic of the blog and a little bit more about what is the 2% voltage drop rule and what you found in doing this research, Lucas?
Sure. So first and foremost, this is kind of a revised edition of an analysis that Paul and Ryan did in 2015, also on the same topic, so the 2% voltage drop rule. And we were rereading that analysis and really wanted to tackle the same subject again, given that we've had another 5 years of equipment and system design advancement. So I want to give them credit. They spurred the whole idea, and I'll let them talk a bit more about that later on. But the core issue here, the 2% voltage drop rule, is something that's kind of hard to define. The way we talk about it in the article is that when pushed to explain what the rule is or why it's in place, most people just say that's always how it's been done. And specifically what we're referring to here is the concept that when you're sizing conductors, the DC voltage drop should be limited to no higher than 2%. So our best guess at the origins of this rule are the earlier days of PV installation. Modules were way more expensive than they are now. System voltages were far lower. So power overall coming out of those PV systems was very expensive. So in those days, it may have made more sense to upsize your wire gauge in order to lose less power through voltage drop. However, we wanted to kind of revisit that idea and bring it into 2020 and see if those same concepts still apply.
All right, and I should have mentioned before we got started that you can submit questions live using the Q&A menu at the bottom of your screen. I'm sure you are all experts at using Zoom by now. So we will be answering questions live, and in addition to the questions that were submitted in advance. And then also the chat, that I'm going to be putting some links as we're talking about things. So I just put the blog article that we mentioned, I put the link in there. And yes, we are recording this session, and we will be posting it to our YouTube channel as well as on our website, and also sending a follow-up to all the people who attended as well as the people who registered and maybe weren't able to attend. We're probably not going to share the slide deck because there's really not much to the slide deck. It's just, you know, this screenshots of titles. The meat of this presentation is really the live Q&A session. So you can find a recording that on our YouTube channel after. So back to our discussion on 2% voltage drop. Explaining a little bit more, so what were the key takeaways that you found in this last analysis?
Right, so I guess taking a step back, we're revisiting the same analysis that Ryan and Paul did in 2015. And the way they went about that was modeling systems in 3 unique sites across the US that represent different levels of irradiance. So Seattle, Atlanta, and Phoenix. We did that same process again in 2020, all using helioscope modeling, where we created a variety of different system configurations using different components at each of those 3 test sites. So we were using 400 watt modules with either 1000 or 1500 volt inverters and inverter load ratios of 1.35 and 1.5 to try to get to about the average system configuration for 2020. We analyzed those and built them in Helioscope, which produces what's called an 8760 output spreadsheet, and that represents each of the 8,760 hours in a given year. So it models system production hour by hour based on historical meteorological data. So we use those spreadsheets to then calculate the real world voltage drop for each of the systems that we had built out in Helioscope, calculated each voltage drop, compared it across sites and across system configurations, and built our conclusions from that. So at the end of our article, we talk about our main takeaways. First and foremost, the 2% voltage drop rule is not explicitly laid out in code. We do want to mention that first, the NEC does talk about voltage drop considerations. It never calls out 2% explicitly, and its voltage drop sections and references don't relate specifically to PV systems. And we do cite that in the article, which I've added a link to here in the chat. Our second main takeaway was after doing all that modeling and calculating the real world, what we call effective DC voltage drop, we found that 2% is far too high of an estimate. In reality, what we were seeing was much closer to a 0.5% DC voltage drop, which leads us to our other main takeaway, which from a design standpoint, our main recommendation after seeing this real world data is that in most cases, you can start with code minimum wiring, and that should be sufficient to keep voltage drop well below the 2% threshold.
Right, and that's something to note that, as you already mentioned, NEC does not address voltage drop in terms of performance. So the National Electrical Code is written by the NFPA, the National Fire Protection Agency. Their primary concern is fire and safety. So they are going to look at, you know, how can you design a system such that you're not going to start a fire or cause some sort of safety concern from an electrical perspective, and make sure that you are protecting life and property. They do not care if your system is performing optimally. So the 2% voltage drop rule is more of a performance issue. If you are not meeting the minimum voltage of the inverter, then the inverter isn't gonna turn on, and that's a problem. So thank you for that summary, Lucas, of the analysis that you did. And if you wanna read more about that, again, the link is in the chat box, and you can also find it on our blog on our website. So we did go, we put out ask for questions. So people did submit some questions ahead of time, and we are going to get into those next. So are there areas where an AHJ or incentives that use the 2% voltage drop rule as a requirement? So Ryan, maybe you can answer this one.
Yeah, so we were having a discussion about this last week, and there aren't any AHJs where, you know, like Lucas was just saying, it's not a code requirement. So it's not something that an inspector can point to and say, you have to do this. But rather where we are seeing it is in incentive programs where an agency that's basically doling out money is going to make sure that the systems are operating as efficiently as possible. And this is one of the ways that they can do it. And so there are some areas of the country where this is, you know, we say it's not really a rule, but it kind of is in those locations because they're going to require that you follow these performance specifications, and that's really what it becomes, is the performance spec. And so yeah, we do see some areas like that. And then when we were talking, you know, this is also a Ken Paul had brought up how there's programs out there that have inverter loading ratio requirements. So similar kind of requirements where you can't overload the inverter, or you can only overload it to a certain percentage, and that's all about performance. And then so the big question, and this is why we wrote this originally and why we are revisiting it now, is do those rules and does the application make sense, honestly, on a whole? And so the other area that I see this a lot is in just system specs. So as a design firm, we'll see system specs come in, and built into the specs from the developer or from the owner, whomever, is this 2% voltage drop number. And so it really does carry over. And so those are not AHJs, those are not incentives, incentive agencies. Those are the people owning the system or writing, this is what the system this is the requirements for the system. And so we do still see them loaded in there. And then the other thing I wanted to point out, and I should have just piped in when Lucas was talking, but everything we're talking about here, we're specifically keeping over on the DC side. The AC side of the system gets much trickier, and the analysis can get much more convoluted, much quicker, I would say. And so, and the reason for that is the inverters have a tolerance. The tolerance on the AC side for voltage input from the utility grid when we're talking about grid direct inverters, is much tighter than on the DC side. And so if you have the wrong, if you have excessive voltage loss or excessive resistance, I should say, in your wiring, then the inverter may or may not turn on. And so it becomes a bigger issue on the AC side, is where basically where the lesson there is.
All right, thank you for that. So in terms of calculating voltage drop, and this is a question that came in from our Google form ahead of time, how does one calculate the average voltage drop for a series of circuits? And is it really just the mathematical average of each individual circuit voltage drop? How do you go about dealing with that? Paul, maybe you can answer this one.
Yeah, and so again, I'm specifically talking about how we do it in Helioscope, but it's, essentially the way it's done is based on the total resistance of the circuits. So when you're looking at calculating the average voltage drop, and again, keep in mind, there's a distinction that comes up in some of the questions, is voltage drop versus energy loss. And in many ways, they're very similar. They're, if you kind of control for everything else, they're basically the same, except that voltage drop kind of implies that you're looking at the same time period. Energy loss is something that you could kind of calculate it for any 1 hour and then just add it up over the year, and then it's just more energy loss. But the way we're doing it is based on essentially the resistance of every conductor. If they're combined, you then of course run greater current through a larger conductor with lower resistance. And actually, by the way, I don't know if there's do we have the slide of that chart that we had from the operating voltages of the modules? Yeah, cool. So this is actually this is from an old presentation that we did. That was actually 2013, I think. We did this for like a Sandia conference. What you're seeing here are just a scatter plot of module. Well, actually, this is because every module is working at a different voltage. How close they are to their ideal. And so basically, when an inverter is collecting, say, a megawatt worth of modules, you might have 100 strings of 10 modules. Again, very rough numbers here. The inverters, a central inverter in particular, is picking the draw voltage that's best for the entire array. And what that means is that your short strings have a smaller resistance, your long strings have a greater resistance, have a longer run and a higher resistance. And therefore, the singular operating voltage for the array is going to be kind of an average. It's going to be the best for the modules in the middle. And therefore, the modules that are closer are going to run lower than their, natively, they'll be running lower than their MPP wants to be. And further away, they'll be running higher to compensate for coming down as it runs through those conductors. So this kind of gives you a flavor for how those calculations are done. So it actually is done on each conductor, each string, and then each inverter, right? This you can see here what happens when you kind of have one inverter that's got a big range of modules and it's got one operating voltage for all of them. And you could visually see that, hey, if I had two, then I'll have kind of two operating points with sort of maybe fewer modules off of their peak. And then, obviously the string inverters would be doing better, modules and power electronics would be doing better. But that's just sort of to answer the question, kind of how things are done. Oh, by the way, quick tangent, speaking of Helioscope, Ryan, you are the second lowest user ID in our entire user base. So we've got a few thousand customers. The highest one, so the user ID is just auto increment, right? Just like any numbering system. The highest one is 158,000 user IDs. So we've had a lot of people churning through trials. Ryan Mayfield is user ID 54. So you are an OG of Helioscope.
Wow. My
question is, no one's going to guess, I don't think anyone's going to guess the person, but do you guys want to try to guess the firm of the one current paid user who has a lower user ID than Ryan does? It's a big firm.
You can go with what, Blue Oak? I don't know.
Good one, but no.
No?
Borrego. Tarn Yates at Borrego.
Okay.
So yeah.
Of course.
So
of course.
Yeah.
Sorry, Tarn.
So
I should have thought of you first.
You have the Helioscope user ID equivalent of the people who have a Twitter handle of Q. So anyway.
I'll take it.
That's
Yeah.
great. I love that. So on to the next question, and this one actually was submitted by Corey Shalonsky. Hey, Corey, thanks for being on the line. And how does one calculate the voltage drop for circuits made up of varying wire gauges? So he's asking for circuits maybe having multiple wire gauges, like say a module or Mlpe having a 10 gauge wire output conductors and home runs being 8 gauge. Is it necessary or desirable to consider the different wire gauges in the circuit voltage drop calculation? Or is that just being overly specific?
Yeah, I'll take this one on. So this is something that we actually do quite often because we work in one of those jurisdictions where the voltage drop is a requirement, actually having to show the calculations on the voltage drop. And so quite often we will have quite a long run, and to overcome the voltage drop, we have to use different wire sizes. And so we do exactly what the question's being asked. So we will go from point A to point B, that's on 12 gauge wire. So we know the resistance, we know the voltage, we know the current, we can calculate the voltage drop of that section of wire. And then we're gonna run a couple hundred feet with that same circuit, but it's going a further distance. We're upsizing the wire, so we're changing the parameters on that circuit. And so the only parameter that really changed was the resistance of the wire, so we'll calculate that. And so then we're just adding up those different voltage drop numbers to figure out what that total circuit is. What this gets into, which maybe this is a good time to talk about it, is, and I know Paul's going to have, and Lucas, that you found some stuff on this as well, but what we're doing when we're doing this, it's really a snapshot in time. And so this is a singular moment, and using these variables in a way that looks at a single point in time. And so when we're using something like STC, we use standard test conditions to do this calculation. Standard test conditions, again, being 1,000 watts per square meter, module temperature of 25 degrees C. Those are the two big ones that impact what we're doing. And those two conditions, very rarely exist at the same time out in the wild. You don't have modules that are in full bright sun at 25 degrees C. You may, tens of, maybe less than a dozen hours a year or something. I mean, it's depending on your location, it's a rare event. And so one of the things that what we were trying to show, and one of the reasons why we did this originally and why Lucas and Nikki looked at it again is, what is the real loss here? And so we have, if we're doing these calculations, we do it at 25 degrees C at standard test conditions. And then we're going to get some number, but that number again is it's not a realistic number. And so with using helioscope and doing the modeling and doing the analysis, we're able to actually look and see, well, what is the actual irradiance on the module when the modules are 25 C, and actually what is, taking into account the temperature rise, the voltage loss of those circuits to be more accurate in terms of what that calculation is. So all to say that, yes, you can do this calculation by hand. You can grab that snapshot in time. But it's going to be overly conservative is really what it comes down to. And Lucas mentioned this earlier. If I remember right, going back into the memory bank here of 5 years ago, what we found almost universally across all three sites, the three different sites were a little different, but if you calculate for 2% voltage drop, you look at the actual losses over a course of a year, and you were actually losing something that was more like 1% effective drop based on the wire sizing. So of course you need to look at your specific site to get those pieces of information, but all in all, to say it's a conservative way of doing it. I don't know, Paul or Lucas, if you have something to add to that.
Yeah, if you could skip forward a slide, Jennifer, I think we have one of the infographics we use in the article here. Maybe one more. Yeah, so we did, so in Helioscope, again, that 8760 spreadsheet output, it measures site irradiance each hour of each day throughout the year. And so we compiled all that data to find the average irradiance during daylight hours, as well as periods of high irradiance and periods where they hit or exceeded that STC irradiance. And this is a graph of frequency distribution across each of those 3 test sites. So you can see that Phoenix obviously gets more sunlight consistently than Atlanta or Seattle, but even in Phoenix, you're rarely crossing that STC irradiance threshold. And we found the average irradiance to be around 730 watts per meter squared, which is again only 3/4 of what they're tested at for STC, whereas in Seattle, we found average irradiance to be about half of what STC is. So using STC for those quick back of the napkin calculations can be useful, but we found this to be a much more accurate estimation of the real world voltage drop.
And just to build on that, like what I think most people are going is, don't forget that it's I squared R, right? So let's just take the Seattle example. When your average irradiance is half, then that means that the voltage drop and wire loss is 1/4 the results of the STC calculation, just because of the way the math works. So it really exacerbates those kinds of dynamics.
Mm-hmm. Yeah, so it sounds like 2% is a way to kind of just not run through all of these calculations, but it is more conservative. And if you're wanting to understand it better, then you need to look at your specific site and look at the actual annual irradiance for that particular site. So what are the best practices for calculating voltage drop, particularly when implementing module level power electronics like microinverters and DC optimizers?
Real quick, I saw that a question came in related to that one, so I'm going to jump back real quick, Jennifer, to grab that question before we move on to MLPEs, which we can definitely talk about. And so Corey asked basically this snapshot in time, what are the values used? So I think we may have addressed it here, but the most conservative would be using max power voltage and max power current at STC conditions. I mean, that's just, wouldn't we all just love to be operating right there all the time? And that would be a glorious thing. What we found, I think, a little bit more realistic is using the NOCT values. And so, you know, using, typically that's 45, and this varies by manufacturer. I believe it's 45 degrees C module, 800 watts per square meter, using those values. And then it could completely be up to your jurisdiction or your rebate authority, because we are, you know, there are some we work in where you have to use temperature adjusted for the average high temperature, the voltage adjusted for the average high temperature at the maximum IMP. So you get, you know, even lower voltage at even higher current. So all to say, you know, if you were to just do one, I would probably use NOCT. STC is the most common. Both of them are still going to be on the conservative side. So
thank you for that. And just for those who might not be familiar with all the million different acronyms in the industry, NOCT stands for nominal operating cell temperature. And I put a little definition into the chat box.
Thank you. There's always that. I always tell people, you know, define your terms before you use them. And then I just go and I'm a really good dad that way. Do as I say, not as I do.
So back to the other question that we just asked. What are the best practices for calculating voltage drop when you are using MLPE, so module level power electronic devices like microinverters or DC optimizers?
Sure. So I think this was a question that was sent in. So I think that the big question here, so microinverters, won't talk too much about it just because that would all be on the AC side. You're not going to do DC voltage drop on the 3 feet of whips coming off the back of the modules. But for the AC side, using nominal voltage and nominal output current. But again, that's on the AC side. It gets into a little bit different considerations. On the DC side, so if you're using a solar edge, for example, something that has a fixed voltage output, the way that we do it and the way that I think has been mostly accepted is using that fixed voltage from whatever that manufacturer says their fixed voltage is. So Solar Edge commercial, it's 850 volts. And then the big question becomes, well, what is the current that is on that line? And so you can use the maximum current that Solar Edge says that their optimizers would put out, but more than likely, your current will be less than that. So the way that we do it, and this seems to be the accepted method, is you have a fixed voltage, you have a certain amount of power. So your string has a certain amount of power, you have a fixed voltage. So you take your power divided by that fixed voltage, that would tell you what your current output is, and you can use that on to do your current output. Again, that's using a lot of assumptions, and that's probably a more conservative method because there's going to be plenty of times, almost all the time, where that string is not going to be putting out that power value. It's going to be something less than that. But it's still at that fixed voltage. So it will ultimately mean you have less current. So you will have a higher result. Your result will be more conservative than reality. And Paul, do you, within Helioscope, are you guys taking you're taking those values into account and when you're doing all those calculations?
Can't stop the photo bombs. Yes, so those are all being factored in. So I would say, just to clarify, we're doing actual production or actual conditions every hour. So technically, Helioscope doesn't do STC and then derate it. We're just saying, well, at this moment, it's, 230 watts per meter squared, and the plane of the array is at 37 degrees C, and therefore the module has this kind of IV curve, and therefore this kind of output. So it's just like kind of it follows the physics through at each hour. So.
Perfect. Yeah, so I think that gets you pretty well on MLPEs in terms of how to apply those different voltages. And then we have plenty of other situations as well where there's not fixed voltages, and so we have SMA and TIGO, for example. If you're pairing those up, and it's not an optimizer, but it's purely there for rapid shutdown requirements, then you're gonna kind of back to the old school methods of your string length is your voltage, and it's going to vary throughout the day. And so it's kind of back to that same thing we were talking about of using STC versus NOCT.
All right. And we have gotten a number of questions that come in beforehand, and there's a few of them that are coming in live asking about the formula for calculating voltage drop and specifics. So you can read more information on how to actually go through the voltage drop calculation in our blog post, which we link to in the chat, and it's also on our website. And in terms of some of the more specific questions of, how do I calculate for this site or this particular wire size, it's site specific. So you have to run through the calculations and do it for your particular site. So we're not able to do your voltage drop calculations on this Q&A session right now. So run through the examples and do the calculations, and then let us know if you have questions. So moving on to some of the questions that are coming in live. So manufacturers have distance limit, or do manufacturers have some distance limitations as well? So for example, and this is just quoting, for example, when designing the installation, make sure to maintain the maximum physical string length as well. The total cable length of the string, excluding power optimizer conductors, should not exceed 1,000 feet, and so forth. So that was for a DC converter.
Yeah, and that one, I see that as well, and I can't say that I've explicitly seen that. 1,000 feet on a string, that's getting pretty far regardless. But my inclination is to think that maybe that has something to do with the communication, the ability for those module level power electronics to communicate properly with the inverter, so that they do execute the shutdown properly, because they are communicating over the power line. So there's going to be some limitations on that. But that's just my gut reaction to that comment. But for sure.
Yeah, but if I can,
of course.
This doesn't address it directly, but what I hear when I hear that is, and again, with our user base, we're supporting a few thousand customers every week, and every now and then we do have people who are surprised that SolarEdge designs can't do everything they ever want them to be. So often, like they'll just be like, they'll just, a certain configuration just won't be possible. You might have SolarEdge min string of 11, max string of 17, and they have 20 modules on the roof. And that's like, I'm making up the numbers, but directionally that happens. And we're like, well, you can't get 20 if your min is 11 and your max is 17. If there's just no, like 2 of 10 is too short and 1 of 17 is not long enough. And they're just like flabbergasted that SolarEdge, they're like, they can't do everything always with all SolarEdge components. And so I think like, that's what I hear in that is like, some people believe that just like, if you're using SolarEdge, you can kind of stretch everything to the limits. And that's, I could see SolarEdge's field engineering saying, hey, look, like voltage drop is a consideration. These things have output voltage range, and we have, the inverter has a certain voltage range, and I think people are doing that on string inverters naturally, and I could see some small percentage of SolarEdge's customer base thinking that they don't have to worry about that part of the physics because they're using SolarEdge. So.
All right, and I guess staying on the topic of helioscope, so how can someone use helioscope to help them with some of the voltage drop considerations for their design?
Yeah. So as I think in a brief reference to, helioscope is doing an annual calculation, and it's giving the results hourly. And so so basically, the way you would do it is design the system as it's built. So that's going to include the modules, of course, as you can see here. And then this doesn't show the electrical circuit system, but yeah, I mean, if you have the inverters and any combiner boxes like located where they are physically, then helioscope's going to have the conductors for those physical distances. The simulation is going to have the results. And as Lucas was talking about, the CSV output is an hourly calculation, and it does report the voltage drop every hour. So that is sometimes, where when people sometimes are most incredulous about this number is too high or too low, we'll just take them to the hourly results and say, let's just look at this hour by hour and get comfortable with whatever it is that they're uncomfortable with. And by the way, if I can make one more promise here, and we didn't talk about this in advance, but I actually want to come back to the concept of effective voltage drop. And what I would say is, I think we should talk about it a little bit more, because Lucas touched on it briefly in the article, but I think it's an incredibly powerful concept. And by the way, I would even say, like, for those that are here to sound smart at the next Solar Beer Club, I think effective voltage drop as a concept is like the way to sound smart at your next like virtual cocktail party. And so I want to kick it back to Lucas. And then as Lucas talks about it, I'm going to promise a helioscope calculator for effective voltage drop. So when Lucas talks about it, we'll provide, for anyone who asks, or maybe anyone who attends, we'll figure it out, a little Excel tool where you can take a helioscope output and then from a little post-processing in Excel, get a number for what Lucas or Ryan, or I can do it, can explain about effective voltage drop. So if I would maybe kick it back to Lucas on the article on that point.
Sure. Jennifer, can you scroll back a few slides to the one with the bell curve? Yeah. So we do this is, again, pulled from that same article. This is just a visual representation of that idea. So again, with our systems we were testing, we set the inverter load ratios to 1.35 and 1.5. And that's another way of saying the DC to AC ratio. So how much power is coming into the inverter versus going out of the inverter. And what's important to note here is those horizontal lines are set at 1.35 and 1.5 DC to AC ratios. Everything below that line is what is actually seen by the inverter. Everything above it is effectively getting cut off because it's being clipped, given that it's above the set ratio. So the voltage drop losses are going to be higher at those higher voltages, which are again being cut off by our inverter load ratio. So what we're calling the effective voltage drop is the voltage drop from that bottom section of this bell curve, not the top area where you would experience larger voltage drops. Our hypothesis is that you can basically disregard those losses in voltage drop because you're not seeing that power that's being curtailed by the inverter anyway. So we don't need to worry about that voltage drop. The effective voltage drop is what should matter. And across all the sites that we tested, that ended up being about 0.5%, versus if you include the entire voltage drop. So including that clipped power, the peak of that curve, the voltage drop about doubles. And again, all this info is in the article, but site to site, the total voltage drop is closer to 1%, but the effective voltage drop is about half of that.
Yeah, thank you for that. And I know that image is really difficult to see on the slide right now, so I'm going to actually pull it up. Let me see if I can share my screen a little bit better. And
while Jennifer's talking about it, just to kind of talk about it,
what's
cool about it is like, yes, looks great, thank you. Okay. Is it? Yeah, it's a little bit philosophical, right? So like, we're talking about physics, but like every now and then you get to some real, like you get to things that are a little deeper. And, you know, like basically as Luke is saying, like at noon here, are the wires resisting? Yes, they are. Do you have, you know, energy dissipation at the wires? Yes, you do. But it's going to be, if it wasn't, it'd be clipped at the inverter anyway. So it's sort of like, it's almost an accounting trick because the physics of the wires hasn't changed, but it's just it's a mindset shift of, if it's clipped at the inverter, we should calculate it differently, bucket it differently, and think about it differently from the times when the wire losses are actually costing you revenue. So yeah, it's a cool mix of like one part physics, one part accounting, or one part physics, one part philosophy.
And just looking at, just to reiterate what Lucas and Paul are talking about in terms of the graphical representation of that voltage drop loss that you're not going to actually see in reality because of the clipping is this tiny little orange section of the graph here. And so when you start looking at below these lines, the 1.5 and 1.35 DC to AC ratio, that voltage drop is this tiny, teeny little sliver along the edge here. So that's what we're discussing right now, which you can see this virtual or graphical representation.
And this was yet another reason that we wanted to revisit the analysis was in 2015, those inverter load ratios were slightly different than what they are now. Again, equipment was more expensive, so I don't know the exact figure. I think it was around 1.2 was what Ryan and Paul tested in 2015. But again, given that modules are much cheaper and utility scale EPCs want consistent production from their sites, we're seeing much higher ILRs, which means more clipping and in essence, a lower effective voltage drop.
Yeah, it was likely, I'd have to go back and look, but I'm going to pretty confident it would have been 1.25, which was the ILR of kind of the day. That was kind of the accepted number right there with that 2% number. And just like the ILR has grown over the course of time. And so this is kind of the same thing. we're talking about performance and what are the real issues with performance, and ILR was right there with the voltage drop issues.
Mm-hmm. And so one of the next questions that just came in live from Hamilton Hutchinson, thanks for submitting your question and thanks for joining us today. Would multiple wire transitions or types of transitions ever need to be considered when estimating voltage drop? So for example, transitioning from PV wire to a type 2 or a different type of wire, would you need to take that into consideration?
Sorry, I just had somebody using our street as a drag race. I was pausing for a second.
Yeah, it's all good. I have ambulances and fire trucks going by outside. I keep trying to mute myself.
So this is an interesting question, and in short, I'll answer it how we do it, and the answer is we don't take those into account. And the reality of the situation is, anytime you do a transition, anytime you do a connection, there is going to be, there will be some increased resistance. There will be a little bit more voltage drop. I have tried very unsuccessfully with the meters that I have to see the difference on those. And so, the difference is pretty minuscule. And the fact of the matter is, really the big consideration would be the type of wire you're using. If you're transitioning from copper to aluminum, then there's going to be a big difference between the copper and the aluminum's resistance. If you're doing a copper PV wire and you're converting it to THWN2, the copper on both sides of that, presuming the wire size is the same, the copper is going to have the same resistance. So the easy, quick answer is no. If you wanted to, get to the NREL answer, there probably is a difference there, but effectively, it's not something that you're going to see in the field.
Okay, one question for you, Ryan, if I should pile on, combiner boxes. So helioscope, we assume combiner boxes are loss-free, which is of course not right. But how much loss is there? Asking for a friend.
That's a great question that I don't know the answer to. And I think fuses are probably, and fuse disconnects and combiner boxes are probably the source of a bigger portion of that wire loss when we're talking about transitioning. What those are, I don't know. Again, the way we've approached it, I know they're not loss free, but we essentially treat them as such.
Do you think you kind of mitigate some of that in being a little more conservative and using a 2% rule, considering there are some losses elsewhere that we're not taking into consideration?
Sure. Yeah, that's in the end, it's we're being overly conservative, and so we would be taking way more into account, in my opinion. But sure, that would be you could call it your hedging your bets a little bit, I guess, or just accounting for some losses that are otherwise being ignored.
Mm-hmm. Mm-hmm. So another great question that just came in from our audience, Gerber Ramos, thanks for joining us today, is asking about bifacial modules. And I'm going to kind of paraphrase his question. How would you go about calculating voltage drop when using bifacial modules?
That one gets, I would say, really tricky. And Paul, you may have, I know you all have been looking at bifacial stuff on helioscope. And the really tricky part is, this is very site specific, and what is the actual gain? What is your bifacial gain? And, that would be a function of the albedo, which is a function of what is the back covering. Is it a white back, white ground mount on a tracking system where they went and they put white rock underneath versus, on top of a, blacktop, or, on top of a carport or something like that, that's 15 feet in the air, and on top of asphalt where the albedo changes not that much. And so in my mind, I should preface this with, I haven't run numbers to compare, and maybe Paul, you have, on these differences, but my gut reaction tells me is that even using like STC values are going to be even conservative, just given that the amount of gain you're getting is, you might, maybe I've seen, references of up to 30% gain, but if we take into account the whole using NOCT for your voltage drop calculations, that assumes a 20% drop on the current output from STC. So you're still, even using STC, you'd be almost presuming a 20% gain right off the top is where I'm going with that. So I guess all to say that I don't have a perfect answer for that. If you know and you've modeled your site and you have an idea of what we're going to be getting at 5, 10, 15% gain, I would be using that in those calculations. But again, it's going to ultimately be conservative in my opinion.
Yeah, and from a simulation point of view, what I would say, so the way it works in Helioskop now is that people can add a bifacial boost, and it's taken year round. And again, in fairness, there are other models that we haven't incorporated that will factor in, just a lot more sophisticated modeling of, as Ryan's saying, albedo, backside reflectivity, things like that. And so what I would say is, to a first order, from a simulation point of view, it will factor in properly, which is to say that if you are going to get, I'll pick 10% only because it's a round number, not because we're saying that's the correct number. But if you're getting 10% more of a backside boost, then that would show up in the module IV curve. It would show up in the simulated current, and therefore the actual, IR losses. And again, because they're a square, it'd be 1.1 squared, which is about 1.11, I think. So you get the extra. Just like we were saying, Seattle having no sun or so little sun makes the actual losses lower than STC. Well, if we're moving the opposite direction, getting more current, then that same dynamic plays in, and the higher current is actually squared. Then the next question, which is outside of Helioskop now, we're working on incorporating it in a more sophisticated way, is does our approach of taking one percentage factor across the whole year, is that accurate or not? And honestly, I'm not close enough to it to have a point of view, right? Like if you're going to get X% boost, is more of that at the midday or edges of the day? And then that goes back to what we're talking about, the effective voltage drop, where if a lot of the boost is going to be at midday, then actually it wouldn't have that much effect on your, it wouldn't have that much impact on your effective voltage drop, because as we were just showing in that chart, you can kind of, from an accounting point of view, disregard the wire losses when you're already clipping at the inverter, versus if you're going to get a lot of the the backside gain from bifacial at the corners of the day, then that would kind of flow through more directly to your effective voltage drop. So I know I'm not giving you like an easy answer, but just kind of at least talking through the dynamics of the calculation. And again, that's, from a simulation point of view, it's doable with those caveats.
And I think it's a great point, and something that I didn't really consider about just the effective loss and the clipping, or the mod inverter output, keeping that inverter output but the output constant. You're very well likely to see some of those biggest bifacial gains in the middle of the day when the inverter's clipping already. And I know I'm driving some people nuts by saying clipping when we should say power limiting, but I think they all know what we mean. And so, we're seeing a lot of the big gains happen at that time, but again, the inverter's already restricting that power anyway, so you're not losing anything.
If anything, if we're now talking about kind of the profile of the power, another dynamic that is, I think, just as important as bifacial, if not more so, in thinking about voltage drop, would be the physical orientation of the modules. So what I mean by that would just be so in ground mount systems, moving more to single axis tracker is going to mean more hours of the day spent closer to STC, and therefore a higher actual effective calculated wire loss. versus fixed tilt, where the modules are just sitting there. On the flip side, on commercial rooftops, trend has been long the case for lower tilt. So we're going from 20-degree tilt to 10 or 5, and dual tilt, where you've got, east-west racking, where, you've got two modules at, let's say, 8-degree tilt nominally. So those are also dynamics that will change. How many hours of the year are those modules at or near their peak versus at lower power levels? And so again, from a simulation point of view, that just happens automatically. So it's you kind of get that for free as long as you just design the system as it's built and then run the simulation. But from a nerding out point of view, it is interesting that trackers are going to increase the voltage drop numbers. Lower tilt usually is going to reduce the voltage drop numbers because you're just there are fewer ideal hours with the sun. So yeah, it's kind of interesting second order effects.
And this is really getting into how do you quantify bifacial gains, which is an entirely other topic, which maybe we'll have an AMA just on that alone. But I did want to just make a note that in terms of quantifying bifacial gains, you have to know not just the module, but the racking that you're using. So if you're trying to figure out what that is, I encourage you to reach out to the module and racking companies that you're working with, the manufacturers themselves, because a number of them are doing extensive testing on just that and trying to give better numbers and best practices for how to actually quantify that. And Nextracker just put out a white paper called Quantifying Bifacial Gains, where they really take a deep dive into that. It's I think 24-page white paper. So even if you're, maybe using a different racking manufacturer, they really get into the nitty gritty of like, how do you even calculate that? And what does it mean? What does it look like? So there's a lot of good information in that white paper, which I'm going to link to right now in the chat. So I encourage you to read that if you're wanting to understand more in depth how bifacial gains should be quantified. And we are at almost at the hour, so we have just a couple minutes left. And I can't ignore Marvin Hammond's comment on LinkedIn. We love Marvin, and he's always needling us and putting in some great comments. So he mentioned, and I'm just going to read this verbatim. He says, there's a lot of room for voltage drop analysis, but it can quickly devolve into a multivariable problem that is just too expensive to completely analyze. Also, on a large system with many stakeholders with different objectives, optimizing voltage drop for one group can make it less optimal for another. So now, in addition to the technical and financial issues, we have infighting amongst the stakeholders about who gets the optimal voltage drop result. And in the end, a lot of these larger projects, the voltage drop limits are written into the EPC agreements and basically resolves to the old 2% rule or some variation of that. So then we're back stuck with it. He does mention it, but it is fun to geek out over the possibility and worth knowing what it can be done. So my question to you is, when is it worth it to actually go through the time to do this calculation, or is it less expensive to just use the default 2%?
I would say that's gonna vary amongst, who everybody on this call and everybody in the industry, how much time do you want to spend on it? How much time do you want to pay for it to get what gains? I think it's worth at least questioning and, kind of needling that a little bit. And so, for example, if there is a 2% spec written by the own system owners or whomever, very often they're not defining what that 2% is. Is that 2% of STC? Is that 2% of NOCT? So you could hit 2%. You can hit 2% in a lot of ways. If you don't tell me 2% of what, I can hit 2% every time. Mm-hmm. So I think it's just worth looking at and considering, and probably where it really does make make the most sense is when you're getting into these much larger arrays. There's, I can't seem to go a whole presentation without talking about NEC. So there is a 2017, there's a new NEC allowance for doing alternative voltage and current calculations. If you're doing those alternative current and voltage calculations, it's probably worth your time to go ahead and at least look at this. And so maybe that's your cutoff. And I just pretty much made that up on the spot here. So that could be a consideration on when you do it and versus when you don't.
All right.
Yeah, and the only thing that I'd add there is, I'm actually going to call back to one of the first comments we had where there's a little bit of a parallel between this and the way we might think about DC to AC ratio. And Ryan made a reference to it earlier, but there at least used to be, and I believe still may be, a province where there's basically where there's sort of a mandated limit of DC to AC ratio of say 1.2. And the intent is pure. The intent is good to have well-designed systems. But the impact is that it is requiring solar engineers to overpay for inverters and take systems off of their optimal economics by a small amount. And so I think like that would be my point of view. And again, Ryan's closer to this than I am, but from our point of view, it's sort of, it's to question the intent. And is the intent quality? Is the intent cost effectiveness? Is the intent just a negotiating tactic? And this is a red herring for something else. But I think the final point that I would make is, I think if there's one value to this, is that we here, Mayfield, Folsom Labs, we don't have really a horse in the race. Like as Marvin said, we're just kind of nerding out on this stuff. But if this starts to build a body online that 2% is not truth, 2% is not a marker of quality, 2% is not necessarily a standard for any good reason, maybe that's a little bit of ammunition to just not have to waste a lot of time, but just like fire back and say, hey, my design's coming with 1%, not 2%. These are some third parties to validate my thinking. And maybe that's being overly optimistic, but hey, we got to start somewhere.
Yeah. Well, thank you all for the discussion. Thanks again, Paul, for joining us on our Ask Mayfield Anything series. For those who are still on the line, or maybe you're watching the recording of this, please connect with us on LinkedIn. We're always putting out content and more things on there, and we love to have discussions on LinkedIn and nerd out about these types of topics. You can also find more resources on our website, mayfield.energy. We have a blog that we're doing, and we're putting out more and more technical content. And you can also reach out to us directly. You can email technical@mayfield.energy with any additional questions. And with that, I will let you all go to lunch. So thanks again, Lucas, Ryan, Paul.
Yeah, thank you.
We'll see you next time. Oh, and I should mention, we're going to do this again. This is a monthly series. So if you're not already joined on our newsletter, that's where we're announcing these things, and also on LinkedIn. So keep an eye out for our next AMA series. It's going to be on tips for designing and installing systems on space constrained and heavily obstructed roofs. So stay tuned for that next month. Thank you again.
Thanks, everyone. Appreciate it.
Thanks, everyone.